So good afternoon. This is Marv Langston with guest speaker Todd Carrico. This is the third in the series that Jim Petrosini and I have been trying to do for webinars to talk about future challenges for the planet, technology, and its relationship to national security and other interesting topics as they arise. In this third series, I'd like to introduce Todd Carrico. Todd and I first met each other back in the late 90s at DARPA, where we were working together. Todd has been involved in artificial intelligence through his PhD program while he was in the Air Force. And then when he became the DARPA PM, he was putting together a distributed bot-based AI platform for logistics. And Todd has been evolving that platform for his company, Cougar Software, ever since then. So Todd is willing to come aboard today and give us his thoughts on the state of AI today, now that it's in a new hype cycle. And we can discuss that further as we go. We shoot for these to be about 30-minute podcasts or webinars. And if we go longer, we'll break it up into multiple parts. So Todd, hello. Thanks for joining us today.
Glad to be here. Thank you very much. Really appreciate it. Appreciate the opportunity to talk about one of the things that I love the most, which is artificial intelligence.
So you and I have had a couple of discussions about how AI went through its cold winter after the 90s, the late 90s, when most of the time back in those days, we were working on AI for image recognition or AI for natural language processing. And today, of course, we see it helping power things like self-driving or speech recognition in our social media or Google platforms or et cetera. So what are your thoughts on where AI is today and where it's going to go from here?
I think we're at a really exciting point right now. We've got tremendous amounts of data in order to train AI and to build decision support systems. We've got computational power, memory, storage that is sufficient to do some of the more advanced techniques that we haven't been able to do in the past. And we've really got sort of the support of the business community, the military community, the research community to figure out how to start putting more of these pieces together. A lot of it really started with the variants of deep learning, which are basically flavors of neural networks, which benefited from the massive amounts of data available. But it's really starting to branch out from there as they're looking at other ways to apply it and ways to combine different AI techniques. So it's a very exciting time for the field. And I think for the world, because some of the benefits of what's coming out of that artificial intelligence explosion of applications is really producing some very powerful capabilities that we've never had before. And I think it's opening new windows and new doors to explore things in ways we haven't been able to do in the past.
So I know you're aware of this, but the Chinese have stated over the last couple of years that their intention is to create significant AI improvements by 2025 and to be the AI dominant country in the world by 2030. So how do you see our relationship with AI and China? Is that a new Cold War race that we got going on, or is it going to be advantageous to both sides of that equation?
I think it is very challenging. Clearly, there are, like with most very powerful technologies, there are applications for good and applications for ill that AI can be used very effectively for. The Chinese are very effectively using it for state surveillance. They're gathering tremendous amounts of data. And, there's concern that they're going to continue to grow their capabilities in artificial intelligence and may not use them for the best purposes. And this is where I think the community at large really has some challenges. We want to be open and collaborative and help advance the state of science in a very collegial way. But when members of that community are looking for opportunities to get new technologies to use them in various ways, you're really in this struggle of how much do we keep in the open? How much do we have, these open conversations about where technology is going and how best to use it and all of that when there's sort of bad actors. But this has been true for so many technologies. from genetic engineering to chemical to nuclear. I mean, all of these have had tremendous power, but also tremendous risk, right? And I think artificial intelligence is in one of those categories where we've got to try to walk that fine line. We want to develop it as a technology and be collaborative, but I think we also need to put some safeguards in place.
So it's interesting to me that we've gotten to a point now where AI has been raised to the level of White House presidential excitement, where they call out the need to continue to bring it to the fore to support our national security and our country's best interests. We see that we have in the DoD, we have this joint AI center, the JAIC, and we have the new command and control effort called Joint Area Defense Command and Control to be the overall DoD AI-based command and control capability, with each of the services contributing components. In the Navy's case, they call that overmatch. But in your own background, because I know you work a lot with the militaries with your platform, how has AI evolved since you first started working on your DARPA platform up to these 20 years later?
Yeah, let me take a step back before I answer that more directly. So artificial intelligence is really this sort of big umbrella of a lot of different advanced algorithm techniques that are meant to emulate aspects of human cognitive reasoning. There's all kinds of different algorithms, some for planning, some for image recognition, some for optimization. That whole field of AI has gone through some fits and starts. When I was at DARPA, the project we were working on is multi-agent systems, which is another vein of the whole field of AI. For a while, agents was a very exciting topic. There was lots of work going on in all the universities. And underneath that, we were doing things like planning and optimization. Not a lot of image recognition. There were some other programs that were working on that. But that, what is now called good old-fashioned AI, was very hot and very exciting. We had some computational issues, we had data issues, but we were able to demonstrate the capabilities of the technology. Shortly thereafter, the scale up of those technologies really didn't come to pass. And as you mentioned, it sort of went into another dark period. In the early 2000s, mid 2000s, they started exploring and revisiting some of the older technologies. I mean, one of them being flavors of neural nets. We now know them as deep learning. And because of other things that were happening in the industry, computational power, availability of data, broadband everywhere, cloud computing, there was some great opportunities for that particular part of AI to flourish. And they found some good applications, image recognition, for example, and it was very successful. And that sort of reawoke the whole area of artificial intelligence, even though that is sort of one small vein of artificial intelligence. What's kind of exciting is the other stuff never really went away. It never stopped completely. It just didn't get as much attention, didn't get as much funding. Now what I think the community as a whole is really wrestling with is, how do we start bringing some of these other things together and start revisiting earlier discussions about architecture and control. One of the big challenges with neural networks of all forms is the explainability. DARPA started a program on explainable AI. We ultimately need to be able to build AI systems that can incorporate many different forms of reasoning and we can trust. And the only way we're going to trust them is if we can sort of understand the whys and the how of them coming up with these answers. So it's really exciting, because if you look all the way back to the ARPA Rome Lab planning initiative, right? That was heavy into planning, and then that sort of died off, and then multi-agent systems came in, and then that kind of died off. Now neural networks are coming in, and there's all kinds of attention around that, but they're starting to hit a little bit of a wall, right? They've found a bunch of very successful application areas, and that's fantastic, right? They've been able to solve some wonderful hard problems, but that class of reasoning can't solve everything, right? It can't perform inferential reasoning, it can't perform deduction, it can't generate hypotheses. So there are classes of problems for which that particular type of technology doesn't work particularly well, right? So as we start hitting the walls of applying it, people are starting to revisit some of the other techniques and saying, well, maybe it's time to start bringing some of those back, or bringing them together with some neural network techniques in this kind of hybrid approach. So it's very exciting because there's a lot of great work going on, and the underpinning is the larger business and government community has really been working hard to make data available to, as you mentioned, think about from a society perspective, from a military perspective, from a government perspective, how do we help the whole field of AI flourish, and how do we find effective applications that can potentially make a dent into some of the big problems that the world's facing today.
Glad you mentioned the explainable AI. I think to the layperson today, most people don't even realize that AI is being applied every time they speak to their Amazon speaker or their Google speaker, and it plays music for them, or they talk to it on their telephone, or most people don't even know that nowadays you can get a universal translator through Google to translate foreign languages. That's all the AI that started from the natural language processing we were doing at DARPA back in those days. And so that's wildly successful. In fact, an Amazon lead of the AI department told me that you could get context 99% of the time out of listening to language nowadays, even in almost all languages, which is a phenomenal achievement. But the other thing that most people don't realize that AI is being applied to is every time we search for anything on the web, it registers what we're searching for, and then that keeps showing up as an advertisement that we see all the time, and annoying advertisements, but sometimes it turns out to be something they might be interested in. So I'm not all that against it, but for the most part, these are not thinking AIs, as you're pointing out. They're one-trick ponies. They're trained to do something, and they can do that one thing very, very well, as long as you don't ask it to do something different. So what is it going to take to move us towards general AI or explainable AI, as you were pointing out?
That's a really challenging question. I think a lot of people are trying to noodle through that right now. There are some who believe that you can just scale up various neural networks, make them bigger and more sophisticated, use what's called transfer learning to be able to have them apply effectively what they've learned into new domains, and potentially keep combining different pattern recognition systems and into one larger neural network. I personally don't think that's going to work, but there's some folks that are exploring that as a possibility. I personally believe that the right answer is more along the lines of what Marvin Minsky was exploring. How do you bring many of these different techniques together? And his was fundamentally an agent-based approach. He actually started the entire field of multi-agent systems. But the idea was, you take any very large, complex problem and you break it down into smaller and smaller pieces. And as you get down to the leaf nodes, you use the best technique for that leaf. And it might be a neural net, it might be a genetic algorithm, it might be an A-star routing algorithm, whatever it happens to be. But the architecture has to break the problem apart. You use all these different techniques, maybe some math techniques, some operations research optimization techniques, everything in your kit bag. And then the architecture helps you put all those pieces back together again. And the reality is, there's no reason why we have to have a single way of breaking the problem. We might break it down 10 different ways and produce multiple answers, and then compare the answers for cost and time and resources or whatever. So there's lots of really interesting ways of going about that. But ultimately, we need to be able to embrace a wide variety of techniques, and we need to have both the architectural technologies as well as the systems engineering methodologies that will let us design, build, and test those systems. And part of the challenge is those systems effectively, or at least could, start creating emergent properties, right? Behaving in ways that is not clear from the individual pieces. So from a test point of view, which ties back into the whole how do we trust and how do we explain, we've got to be able to have mechanisms integrated into the architecture that will help us understand how it created that solution. What are the pieces that contributed? We need to be able to ask questions of that answer and be able to pull them out of this very complex interaction of components. And the hardest part is, we need to be able to have some guardrails on the system so that we know that the answer is within a defined space. when you start getting into very complex dynamic systems, it's almost impossible to do an exhaustive analysis to ensure that you will always get the right answer. So sometimes what you need to do is create the guardrails around the solution space and basically say, we are going to ensure that any answer it comes up with can't exceed these bounds. It's much like the fly-by-wire for an F-16, right? There are control surface limits that aircraft enforces, because the aircraft can do what you want it to do, but it will tear itself apart, right? So they put control surface limits on it. And we need to be able to do the same thing with our complex systems. We need to be able to accept that they may generate solutions that we don't totally understand. They may be able to explain aspects of it, how it got there, but we won't necessarily in advance be able to compute the stability of the system, but instead need to trust that the system architecture guardrails will protect us from instabilities or essentially tearing the wings off the system.
I love that analogy because it's easy to understand. You don't want to allow your self-driving AI to rip your wings off your airplane or crash your car. But when you're talking about something like command and control, where you're dealing with deploying forces and deploying weapons, how you get the AI to do the right thing within the right limits for that much more complex problem is very, very interesting and challenging. Let me shift it for a second. I'm fascinated by some of the work I've learned about with Tesla doing their full self-driving, because they've made a company decision, or I guess you could say Elon Musk has made a decision to make that full self-driving based only on cameras. So basically by video or imaging, just like our eyes are the way we move around along with the rest of our sensors. So other car manufacturers are doing similar kinds of applications, but they're applying LiDARs and radars and cameras in combination to make their full self-driving. But Musk seems to be thinking that if he does it with cameras only, he can basically apply the resultant technology that they get out of that to robotics in general, so that you could have basic robotic vision. What are your thoughts about that?
I think that's a really interesting area that they're exploring. And I'm kind of torn, because on the one hand, we as humans, we only have two ocular sensors, they're separated so we can get stereo vision, and we are able to perceive and navigate the world very effectively. So, there is an argument for not needing, LiDAR and radar and all these other things in order to be able to navigate the world. But from the cognitive psychologist side of me, there's a piece missing in just the image recognition part. So we as humans form these internal models of ourselves, of our environment. We see the kid at the side of the street with the ball, and we create a mental model that says, which direction is he going? Is he holding or throwing the ball? Is there a chance that he's going to go out into the street because of whatever game he's playing? We do this very, very fast, right? And our mind is constantly updating these models as we're moving around and driving around.
Yeah.
Unless there's an underlying model behind that image recognition piece, I'm not convinced there'll be the richness of understanding and of being able to anticipate the way we anticipate, right? And maybe they can build that in, or maybe they can't. But without that piece, I'm not sure imagery alone is going to be able to do what humans do when we drive, which is we're constantly evaluating and anticipating who's going to cut us off, who's going to swerve on their bike in front of my car, right? Which is why we are very effective. You're going to need to, I think, get at least the equivalent of that in a self-driving car, or we're going to see, a lot of kids playing ball at the side of the street getting hit unnecessarily.
It's a great point, and I like the way you laid that out. And of course, if we relate it back to us, what we do is we run all of our sensors all the time. So we have a model of the ball and the kid and the noise and the sound and the smell and the vision, even though we're dominantly vision animals. So we aren't doing anything with just vision the way he seems to be trying to do it for full self-driving. They must, and to your point, have at least a model of the objects that they think they're seeing, so that they could decide whether or not the dynamics of a car or a kid or a ball is going to intersect with the dynamics of the vehicle at that particular time. So it'll be very interesting to see how this unfolds as it continues to unfold among the auto manufacturers. And of course, the other challenge for them is they want to make these systems as low cost as possible. So every time you have to add a LiDAR or a radar or anything else, then you're adding cost to the vehicle, and they worry about that. So let's shift the discussion again and tell me a little bit about your current platform and how you're using that platform to support military AI and the kinds of military AI you're thinking about.
Absolutely. So, I'm a big fan of Marvin Minsky. The work that we did at DARPA was really built around, some of his concepts of multi-agent systems. So we've been carrying that forward, and basically we're building multi-agent systems that are designed for planning and execution, are able to do data curation, are able to do deep situational reasoning. Some are controlling autonomous systems, the higher brain functions of autonomous systems, where we're building the situational models and trying to understand the behavior of the system over time. We've created a core capability around a hybrid knowledge graph that lets us maintain all of the rich relationships of the data, whether it's for planning, where the knowledge graph is basically the plan, the environment, the resources, or for being able to cleanse complex data, it's the relationships to contextual information, reference data, and various other things. But the key in everything we do, though, is each of the agents is a specialist at doing a piece. And we give that agent the processes and the knowledge and the algorithms and everything it needs to be an expert at doing something. So we've got one agent that is an expert at routing, and he's got an A-star routing algorithm, and he has access to that data and all that. And that's all he does. He's an expert at that one thing. But what makes our systems very powerful is there's other agents that are doing other parts of the problem, and when they need something routed, they request it of him and give him some information, and he comes up with multiple routes that are optimized for various parameters and can provide that back. So this distributed tasking and being able to communicate and decompose these problems and fold them back in again, I really think, and we're not anywhere close to general AI yet, but I really think that's the path. And if you look at some of the things that industry is doing with microservices and REST JSON interfaces and all those kinds of things, it really is starting to move us in the direction where we can now have lots and lots of small agents. They might all be within a company or outsourced or whatever, but really what we're doing is we're assembling little chunks of expertise. And if we have a way of breaking a large problem apart, we can apply this expertise to solve various pieces of it and then put it back together. The things we've been able to do are pretty impressive. And one of the things I love is we've not just been sort of developing the agents, but we've been developing the architecture and the methodology so that we can build larger and more complex systems. And one of the things that we're getting pretty excited about is basically turning the technology on itself, right? So if you've got this kind of planning, reasoning, situational understanding technology, could you use it in the design process, right? Essentially use this kind of AI technology to design and build AI technology, right? So, down the road, it's called model-driven architecture, it's one of the things that I think will ultimately allow us to get through the limits, us as a community, because we continue to suffer from the complexity problem, right? We design larger and larger systems and nobody can really understand it, and they start getting too complex, and security problems start coming in and stability problems and all of those kinds of things. We need to be able to have very large distributed complex systems be built in such a way that we can have trust, reliability, maintainability, security, right? All of those abilities we've always dreamed of, but when you've got, what is it? The F-35 has 25 million lines of code or something like that. I mean, you get systems that big and there's just no way a human can understand the complexity of those systems. Well, we have tools to help us, but ultimately it's still the human designing and building. So, the ultimate is, okay, if you can get this reasoning and automation technology, have it help you build it. Have it find all of the code path flaws and the instability points and the edge conditions, right? So that you can build better systems. So, we're building decision support systems right now, but I think we're laying a foundation that will ultimately let us build even larger, more complex systems, potentially achieving some degree of MDA.
So that is fascinating, and I know you're working hard to do that. You mentioned in passing there the idea of using AI just to do data cleansing, because using AI ML processes is very dependent on good data, and getting good data, I know, is one of the hardest things any of our systems have to worry about. So just say a little bit about what that means, because it seems to me like breaking AI down into smaller tasks and making an expert in smaller tasks may be a better, quicker use of it than when we try to apply it to these giant complex problems.
Yeah, exactly. So we're pretty excited about this, and this is still in sort of the advanced prototype stage. So it's not a full up product yet. I'm really not. This is not trying to be a sales thing. But what we've been able to do is basically go back to sort of Claude Shannon first principles of information theory, and build a system using these agents where each agent is looking at different aspects of the data or relationships of the data, the forms of the data. So if you look at a large structured data set, even if it's got lots of errors and lots of problems, there's underlying patterns, right? There's patterns in the identifications, there's pattern in the value ranges, there's patterns in the spread of errors. There's all these interesting underlying patterns. And today, most organizations are spending 25 to 35% of an AI project's budget having their data scientists work with their SMEs to write a whole bunch of R scripts or Python scripts to try to cleanse the data. It's a very time-consuming, very expensive process. But what they're really doing is understanding the nature of the underlying data and developing, again, pattern-based techniques to try to cleanse or to filter or to repair. They're cross-correlating columns or sets of columns against other reference data to try to fill things in. None of that is very specific to the data. And none of that is something that can't be automated. So we're looking at taking each echelon of that understanding, characterizing the type, characterizing the format of it, characterizing the relationships between columns, and just you keep building and building, each piece trying to add just a little bit of metadata, a little bit of insight into the form, structure, and relationships until eventually you can understand enough to now start making some assertions. And once those assertions start getting generated, now your SME, skip the data scientist completely, your SME can come in and say, yes, that's a correct assessment. Yes, that is an address field. Or, yes, there is a correlation between these two fields. That's a part and that's the part price. So these insights don't need to be told in complex schemas and all of these kinds of things. The system is basically figuring out the context and semantics of the data itself from first principles, which if you can take that all the way through, could give us a completely new way of cleansing structured and semi-structured data without requiring any scripting. And the neatest part about it is once you've gone through this process with a large data set, the agents learn, right? They've learned the patterns and structure of the data. So now you can basically throw away that large corpus of data. You've got the rules. So now you can attach those rules to a streaming set of data, streaming transactional data or sensor data or whatever it happens to be. And they can keep applying those rules, essentially repairing in situ, which is really cool.
So that's interesting. I've in the past couple of years, I've interacted with both some of the big AI players like Oracle and Amazon, and looked at the functions that they already offer to do similar kinds of things. So you can set a set of data into one of their services, and their service will decide what's the best kind of AI tool to use on the data, and then what is in the data. They'll let you know things about that data so that you'll know what is in it so you can move further from that. How does that kind of service differ from what you're working on?
So I think we're trying to be left of that. So we're trying to prepare the data that would go into that kind of AI tool. So what you're talking about is the different forms of data, retail transactional data versus language data versus free text, they all have different properties and characteristics. And because of that, different network structures and different weighting techniques and things like that, training techniques, feedback recognition components, are more effective. So what their system is basically doing is trying to characterize, given the type of data, the structure, the schema, all of that, what's the best technique, so that you don't have to figure that out or try some stuff and then figure out it's not going to work very effectively. They've already characterized and classified all of that. So it's a matter of you characterize your data and it says, oh, well, here's the best one for you to use. And let me go ahead and set it up with a standard set of weightings and all of that to kind of get you started, which is fantastic, right? These are, as engineers, as we start to mature these fields, right, we get better and better tools, we get more automation, and it just allows everything to go faster and be more successful, which is wonderful. But up till now, we still had challenges on just the data prep side, because it requires lots of data scientists and lots of SMEs, and they have to kind of get together and understand each other, right? You've got to train the data scientists to understand what the data means, and then they've got to write the scripts. And typically that goes through many cycles until they can get it clean enough to then go to the next stage, which is what you're talking about, which is starting to actually put together the models that will allow you to then do the training and start evaluating the effectiveness.
Yeah, so that is very fascinating, and I hope you have great success on that. So, given that we're passing our 30-minute mark, let's wrap it up with a couple of thoughts. You and I have talked a little bit about the new book I just finished reading by Jeff Hawkins, 1,000 Brains, and it's very interesting to learn in the end of that, after he talks about how he thinks that they have much more knowledge about how the brain works now than they did 10 years ago when he first started his first book about the brain. But he's now saying that he thinks that we can train machines to have consciousness, and he describes what consciousness is. And then he talks about why we don't have to be afraid of these machines taking it over. So maybe we'll have to have a follow-on discussion about his ideas and the related thoughts about that.
I'd love to. I'd love to.
So any last thoughts you want to impart to the audience?
I think AI, like so many other great technologies, is extremely powerful, but it doesn't, it's not a silver bullet. It doesn't solve all problems. When we talk about artificial intelligence, one of the things I would stress is you got to remember there's a whole bunch of different flavors of that. So if you're really talking machine learning, then there's a broad class of problems that machine learning is fantastic at. But if you're really talking about machine learning, you can't assume that every problem can be solved purely with ML. So you got to kind of peel back that AI onion just a little bit and understand the nature of the problem and the specific technique. If you're looking at having somebody help you design and build a system, right? And is that technique the right technique or in the family of right techniques for the problem you're trying to solve? We've seen lots of times people try to use a hammer on a screw and it doesn't work particularly well, right? And AI is an entire kit bag. So make sure you're using the right tool for the right thing, and explore it. It's very, very powerful. I think it's going to transform our entire world. And I'm really hoping that we can get far enough this time that A, we don't fall back into winter, and B, we actually have a shot at solving some of the big problems we have today. Pollution, energy, clean water. There's lots of challenges that we as a society have, and maybe AI can help with some of those. And I'm excited to be a part of that, and I hope this time we don't start seeing the snowflakes.
Well, I really appreciate and thank you for your time today. I think you're doing phenomenal work with the AI technologies that you work with every day, and I hope that you have major breakthroughs over the next days, weeks, months, and we'll get you back on to talk about it a little later when we can.
Thank you very much, Marv. I really appreciate the opportunity, and have a wonderful day.
All right, thank you.